Okay, so this very last video is on the last two topics that we learned, which are probability and statistics. So we're going to start with some probability. The basic formula for probability to calculate it is the number of ways an event can occur over the total number of possible outcomes. So to give an example of an event that we might try to find the probability of, we talk about rolling an even number on a die. So notation-wise, we use the letter P to represent probability, and then inside the parentheses, we explain the event. So I'm looking for the probability of an even number. Okay. The number of ways that can happen, well, there are 3 even numbers on the die, 2, 4, and 6, and 6 total numbers on the die, so 3 over 6, which can reduce to 1/2. Now, 2 different types of events. We can have independent events, which means that the outcome does not affect the outcome of later events. Okay, so for example, if I have a spinner, 4 equal sectors, yellow, blue, green, and red, and I want to know the probability of landing on blue twice. So we're going to land on blue. They have 4 equal sectors, and of course, it's independent, the 2 events. Okay, landing on blue once doesn't change the likelihood that I'll land on blue a second time. So both of those probabilities are going to be 4. Now, I want that to happen twice. We've talked about ands and ors. So if I want to land on blue 2 times, then I know I have to land on blue first and second. And means that we're going to multiply those 2 probabilities together, so we get 1/16. Now, this is as opposed to dependent events, where the outcome of the first event actually is going to affect the outcome of later events. So for example, I have a glass jar with some marbles, and I want to know the probability of choosing a red marble and then a green marble without replacement. And this idea of without replacement really is what makes this dependent, because once I take a marble out, that's going to change the probability of choosing another marble later. So I want the probability of choosing a red and then a green. The probability of choosing a red, well, we had 6 red total in the beginning and 22 total marbles. And so we multiply. And then the probability of a green, now if I don't put back the marble, well, then the probability of a green is changed. Okay, I only have 21 marbles left, so 5 over 21. And now we're going to multiply, and I can reduce. So this is dependent events. All right, fundamental counting principles. The basic idea is that I multiply my number of possibilities. So as an example, at a deli there are 4 different breads, 5 meats, 3 cheeses. I want to know how many different possibilities there are. So if there are 4 breads, 5 meats, and 3 cheeses, I'm going to multiply those things together. 4 times 5 times 3 is going to give me 60. Okay. Related to this is what's called a tree diagram, which is kind of a visual representation of the fundamental counting principle. So I can show all of my different options. So for example, I have 4 different breads, and I can represent them this way. And depending on which bread I choose, okay, 1, 2, 3, or 4, I have an option for 5 different meats. So each bread has those options of 5 meat. And then from there, I also have the options of 3 different cheeses. Okay, so we've got the tree diagram, which really lists all of our possibilities. Okay, yes, they get a little crazy down at the bottom there. Okay, but I should notice that I should have exactly 60 total options at the bottom, and if you count along the bottom, you'll notice that that's the case. Okay, so permutations and combinations. Basic rule, permutations when order does matter, combinations when it doesn't. Now, notation-wise, when you're looking at a permutation or a combination problem, we see a notation that looks like this. So you'll see a big either P or C, depending on whether I have a permutation or a combination, and then 2 little subscripts. The number in the front talks about the number of elements or things that I'm choosing from, and then the little subscript after talks about the number of things that are being chosen. Okay? So to tell the difference between them, I want to know, does order matter or not? So in the first problem, 4 desserts from a menu of 10. Well, the order that I pick them doesn't matter. I'm still going to get them all, which means that I do have a combination here. Okay, I'm choosing out of 10 4 desserts, so that means I'm going to have 10 C4. As opposed to the second example, 12 runners, they come in first, second, and third place. Well, I'm sure that the person in third place and the person in first place will care if the order gets changed. So the order definitely does matter, so we have a permutation. 12 total runners, 3 of them being chosen, so 12P3. Now, as far as how to calculate these things, 12P3, so when I'm calculating a permutation, we start with this first number and we count down, we multiply the second number of spaces. So for example, here we have 12 times 11 times 10. So again, we start at the first number, and the second number tells me how many spaces down I want to count. Okay, so 3 spaces down, 12 times 11 times 10, and we just multiply, and we get 1,320 different combinations of first, second, and third place. A combination, slightly different. We're going to split this up so we use the same two numbers, but a permutation in the numerator, and then the factorial, that's that exclamation point if you remember, of the second number in the bottom. Okay, so 10p4 on the top, counting down from 10, 4 places, and then 4 factorial on the bottom. And don't forget, factorial means we're multiplying by all of the numbers counting down to 1. Okay. Now, if you're doing this by hand, you can spend a little bit of time doing some simplifying. For example, 4 times 2 in the denominator is 8, so those can cancel. 3 in the denominator goes into 9 3 times. So we can do a little bit of simplifying before we actually multiply together and get the answer. Now, kind of related is we talk about different arrangements with repetition, if I have a repetition within my arrangement. Okay, so for example, how many ways can you rearrange the letters in the word statistics? Now, as a general rule, I want to take the number of objects, or in this case letters, factorial, over the number of repetitions, factorial, and we're going to repeat that for however many different repetitions we have. So in the word statistics, if you count, we have 10 total letters, so I'm going to have 10 factorial on top. But then I want to care about the repetitions. I want to know how many different repetitions do I have. So for example, the S's. I have 1, 2, 3 S's. So I'm going to have a 3 factorial in the denominator. Then I also have 1, 2, 3 T's. So I'm going to have another 3 in the denominator, 3 factorial. And finally, we have 2 I's. So we're going to have a 2 factorial in the denominator. And this takes care of all of my repetitions. Okay. So then to calculate that, we've got a lot of multiplying going on here. Again, you can do some kind of limited canceling out if you like. 3 times 2 times 1. Here 3 times 2 can cancel out with that 6. The 2 here can go into, say, the 4, leave a 2, and then we just multiply what's left over in the numerator. Okay, so in this case, 50,400 different ways to arrange the letters in the word statistics. Okay, so that will bring us to statistics, which we're going to start with different types of data. So quantitative versus qualitative data. Basically, to tell the difference, the question you want to ask yourself is, can I measure it? Is this something I can put a number to? Okay, quantitative is going to be numbers, whereas qualitative is going to be descriptions. So for example, in this particular problem, senior class, 578 students, 236 of them are honor students, 150 scholarship winners, 51% male. All of these different things, okay, honor students, scholarship winners, male versus female, all of these are descriptors. I can't actually measure or put a number to any of those things, which means that these are all qualitative measurements. Univariate versus bivariate, well, you should be seeing these prefixes which are useful. Uni meaning 1, and bi meaning 2. So univariate means I'm only gathering data on one type of thing. Bivariate means I'm gathering data on 2 different things, and then looking for a relationship between them. Okay? So in the example, Mr. Benjamin tries to see if his students' shoe sizes are related to their heights. The question is, how many things am I measuring? Well, I'm measuring shoe sizes, and I'm also measuring heights. I'm measuring 2 things, makes it bivariate. Okay, now summarizing data. Just as kind of a recap, different measures of central tendency. We know the mean is the average. We can calculate it by taking the sum of the values and dividing by those number of values that there are. The median is the middle number if I arrange all of those numbers in order. The mode we know is the most common. And the range is the difference between the max and the min. The range, of course, isn't technically a measure of central tendency. It's talking about how spread out the data are. All right, so different ways of representing data. One is the box and whisker plot. Okay, it looks kind of like this. We see a box, we see whiskers. the important pieces of the box and whisker plot are that 5 statistical symmetry that we talked about in class. Okay, the 5 important pieces of information are the minimum, the first quartile, the median, the third quartile, and the max. Okay. Quartiles, the fact that we're using quartiles is a big hint as to really the main idea behind the box and whisker plot, which is that we're splitting the data up into quarters. So each section of this box and whisker plot represents 1/4 of the data. Next thing we want to talk about is a histogram. This is basically a bar chart that shows me some different frequencies. Okay. In a histogram, we always have frequencies going up along the y-axis, and then intervals of some sort going along the x-axis. Okay, and then we can visualize sort of how different intervals relate to one another, whether one's higher than another, one is more frequent, so on. Finally, a stem and leaf plot. Stem and leaf plot looks something like this. This is an example, and it helps me organize my data, but it also, the nice thing about a stem and leaf plot is that it doesn't lose those individual data values. So I can still tell exactly, say, what the mode is in a stem and leaf plot, but I can also say, well, what's the most common? I can see the longest string of leaves. Okay. The one thing we want to make sure that we remember about the stem and leaf plot that's kind of easy to forget is make sure that you always write in a key. Okay. So that we can explain what each data point means. So the 6 on the left and the 0 on the right means the number 60. All right, moving right along, one more type of chart that we might have is a scatter plot. Now scatter plots, we know what they kind of look like. They look like a bunch of points like this. And the idea is that we've got bivariate data, again meaning 2 different things that we're measuring, right? And each pair of data is 1 point. Now, related to this, very often when I have a scatter plot, I want to see how the data trends. I want to see what direction it's going in. And so we can create what's called a trend line, okay? Sometimes also called the line of best fit or the regression line. And that can help me sort of draw conclusions. If I have a data point that I want but don't know exactly, I can use my trend line to estimate where I expect that data point will be. Now finally, when we have scatter plots, we want to talk about correlation and how the data points relate to one another. So a couple of different types of correlation. Positive means we're going upwards from left to right, in a kind of general upwards direction. Negative means we're going in a, basically a downwards direction as we go from left to right. Okay. Whereas no correlation means that I really don't have any kind of relationship. I can't say I'm going up, I can't say I'm going down. It's really just kind of a big mess in the middle. Strong and weak. Strong means that the points are very, very closely in a line. Okay, they fit a line very well. And weak means that they're a little bit spread out. I can still see a kind of trend, either upwards or downwards, but less strong. All right, just about to the end here. Just some practice making some of these plots that we have. So I want to create a box and whisker plot and a stem and leaf plot. Now, one of the things about both of these types of plots is that the first thing I want to do is put all of my data in order. So you might want to take a second, maybe pause the video and copy this down, or try it on your own, see if you can put it in order. Now, for the box and whisker, what I want to do is find that 5 statistical symmetry, those 5 kind of key points. Now I have an even number of data points, so the median is going to be in between 2, but in this case kind of nice because it's in between 2 64s, the median is 64. Then what I've done is I've split my data into 2 halves. So to find the first quartile, I want to find the middle of this first half, which is here at 60. Same thing with the third quartile, it's going to be the middle of the second half, so 68. And then the min and the max are easy, those are the first and last problems. So now that I've got that 5 statistical symmetry, I can get my number line all set up, and I can create my box and whisker plot. Notice that my minimum is down here. It has a little dot. The first quartile and then the third quartile, they have a box in between them with a line down the middle at the median. And finally, another dot at 74, which is the max, and my whisker is going out to the min and the max from the box. Lastly, the stem and leaf plot. So my stems are the first digit of each number, each data point in here. So I have 50s, I have 60s, and I have 70s. So my stems are 5, 6, and 7. And then for each, now that I've got this all in order, it's pretty easy to write 55, 59, 59, and so on, and figure all of that out. Once again, don't forget your key. It doesn't matter which point you pick from the stem and leaf plot to make your key, just make it something that's actually in here. Don't put in 100 if 100 isn't in your stem and leaf plot somewhere. So that's basically it. Congratulations, you have made it to the end of your final exam review. Best of luck with the rest of your studying.